Alright guys, so we're moving forward in our biochem unit, and the next lesson is going to be on the properties of water. This is definitely, once again, something that you have seen more than once, but we need to make sure we have good solid background before we get to macromolecules and then move into the cells. So, sorry, I'm doing this from the wrong slide. So really we could have grouped this with the chemistry, but we didn't want to make the lesson too terribly long. So we're going to talk about a few important properties of water that help to make water conducive to life, and it really does make life possible. So we know that the majority of our bodies and the majority of our cells are actually composed of water, and like our cytoplasm is just a giant solution with water and many other substances dissolved in it. And so water is essential to our existence and essential to us continuing to survive and thrive. And so this is going to be all about some of these special properties that water has. So number one, just kind of going back to our lesson from yesterday on chemistry, we talked about polar molecules. And a polar molecule is one in which covalent bonds hold the molecule together, but in the sharing in that covalent bond, the sharing is unequal. And so water is a prime example of one of these polar molecules where the electrons are not shared equally in a covalent bond. And so what happens is certain areas or poles form in the molecule, and they're going to have these partially charged regions. So in the case of water, oxygen has a very high electronegativity, and what that means is it has a higher affinity, or it likes electrons more than the hydrogen atoms that are bonded to it. And so the hydrogens really don't have a strong attraction. And so anytime we have polar molecules, it's always going to be the other element that is hogging the electrons from hydrogen. And so in the case of water, oxygen hogs the electrons. And so what happens is those electrons are hanging out closer toward this end of the molecule. And so what we see are these partial charges. So the oxygen end of the molecule becomes kind of negative. That means a partial charge. And then the hydrogen ends become kind of positive. So remember, these are not ions because we don't have a full-on positive or negative charge. We're not losing or gaining electrons in the case of ionic bonds. They're just simply not getting shared equally. And so we have these partially charged regions. And so, as we talked about yesterday also, when we have these polar molecules with these weak charges, it allows for the formation of hydrogen bonds to form in between them. So your covalent bonds are within the molecule and they're really strong. Well, these hydrogen bonds form between the molecules and they are very weak. And the reason hydrogen bonds are weak is because they are attractions between weak charges. So we have a kind of negative and a kind of positive. And so hydrogen bonds are going to be an attraction between these weak charges, and therefore the hydrogen bonds are very weak. That doesn't mean they're not significant, okay? As we saw in our notes, we know that they're important because they hold water together, and these are the properties that we're going to talk about today, but they're also important in molecules like DNA and proteins. And so even though they're weak and they're constantly breaking and reforming, they give water its unique structure, and we're going to go over some of these properties. Now, one property is that water is sticky. Okay, water demonstrates both cohesion and adhesion. Now, cohesion is when water sticks to itself. And so back freshman year, you did a lab where we put drops of water on a penny, and we tried to see how soap would affect the surface tension or the cohesion of water. And so without soap, we were able to put quite a few drops of water, and what happens is that water just beads up and it just grows and grows and grows on the penny. Now, once we added soap, it actually decreased that surface tension and the water ran off more easily. But when water sticks to itself, it does create this surface tension. And that's why, like, bugs can sit on top of water. You can float a paper clip on top of water if you evenly distribute the weight. And so water sticks to itself, creating surface tension. Now, the other sticky quality is that water is adhesive, and that's the fact that it sticks to other things. And so this is really important for life, but especially when we talk about plants, because it gives the ability for water to climb up tubes. And so when we talk about plants and we know the importance of water to plants, this is what allows the water to travel from the roots all the way up to the shoots and the various parts of the plant. The combination of cohesion and adhesion, water sticking to itself and water sticking to other things, is very important in many different aspects of life. Now, when we talk about adhesion, this creates capillary action, and that's just that natural tendency for water to climb up tubes. And the thinner it is, the higher it will travel. This is also the reason that you get a meniscus. So here you can kind of see how that water dips down. I'm sure in your science classes you've had to read graduated cylinders, but the reason you get that dip is because the water is sticking to the sides of the graduated cylinder. And so not only does water stick to itself, but it also sticks to other things. And that goes back to the hydrogen bonding between water molecules. So here's just kind of a quick comparison of the two. Okay, so cohesion is water sticking to water. Adhesion is water sticking to something else. This is a picture of what's going on in a plant. So this is the xylem. This is your water transport tissue in your veins of plants. And so we can see that cohesion, once again, is water sticking to water. And then adhesion is water sticking to the sides of that tube. And then here's just another picture of water sticking to water and water sticking to another substance. All right, another important property due to those hydrogen bonds is the fact that ice will float. This kind of goes against your norm of solids, liquids, and gases. Typically, solids are more dense than the liquid form. And so if you were to put a solid in a liquid of that same form, it would sink. But when you put ice in water, it floats. And this goes back to the hydrogen bonds. Once the temperature begins to drop to around 4 degrees Celsius or below, these hydrogen bonds actually kind of stabilize and they hold those water molecules further apart from each other. So you can see down here what's going on in cold water versus warm water versus freezing water is the hydrogen bonds actually create this lattice-like structure, and so it actually makes the solid form less dense than the liquid form. And so this is the opposite of most substances, okay? So it's something that's kind of unique to water, and so the ice will float. Now, obviously that's not that significant when you're talking about ice floating in your beverage, but it is important for living things who live in bodies of water. Because if ice were to freeze and kind of go from the bottom of the body of water up, that would not allow for life in that body of water in freezing temperatures. But because ice floats to the top, it actually acts as kind of an insulator and keeps that water below from freezing. And so that allows those aquatic organisms to continue living in that environment, even when we do have really cold temperatures. Another important feature of water is that it has a very high specific heat. It takes a tremendous amount of energy for water to change temperature. And so this high specific heat is actually a measurement, and I'm sure you did calculations of this in chemistry, but you can see it's so many joules per kilograms Kelvin. And so if you compare that to other things like sand or asphalt, you can see that this number is much, much higher. And what that means is it takes a lot more energy to raise the temperature. And this is really important to ecosystems because anytime you have climate around a large body of water, it's going to be more moderate. You're not going to see as extreme changes in temperature because the temperature of the water affects the temperature of the air. So it actually kind of is really important for keeping temperature stable. And like we mentioned earlier, the majority of our cells and body are water. And so this is important because we wouldn't want a constant fluctuation of temperature in our bodies. It also gives rise to evaporative cooling. And so water has a high heat of vaporization. And when that water does turn to a vapor, it actually allows those molecules to leave as a gas, which has a cooling effect. And this is important for us in terms of temperature homeostasis. And so just by being a little bit more stable in its temperature, there's a lot of important aspects for life due to a high specific heat. Water is also a really good solvent. So just as a quick review, when you have a solution is a mixture between two things. It's just a physical mixture. So we have the solvent and then we have the solute or the solute. The solvent is what does the dissolving. And most of the times when we're talking about cells and living things, water is going to be our solvent. Water is the solvent in our cells. And then the solute is anything that's being dissolved in that. That could be salts, that could be sugars, that could be ions. And so water actually makes a very good solvent. Sometimes it's referred to as the universal solvent, but it doesn't dissolve everything, okay? But it does dissolve many different types of solutes. Now, it depends on the solute and whether or not that solute is either hydrophilic or hydrophobic. So these two words describe whether something is water-loving. Hydro is water, philic is loving. So these are the molecules that like water. And what happens is the water is able to kind of surround that substance and break it up. And so things that are hydrophilic are going to dissolve in water. Now, these are going to be your ionic compounds or your salts, things like sodium chloride, because the water can easily make those compounds dissociate into their ionic form. Or other polar molecules. Like dissolves like. Okay, so because water is polar, it will dissolve other polar molecules. Now, some substances, though, are hydrophobic, and these are the things that are water-fearing, and these are the ones that are not ionic or they're non-polar. And so what happens is they actually repel the water and they don't dissolve, and these would be things like fats. When we get to our macromolecules lesson, this is going to be a key feature of our lipids, is that they are hydrophobic. So here once again we have another comparison. So here's the difference between a hydrophobic surface. You can see that that water does not spread out as much. Here we have a hydrophilic surface, okay? And then here's what happens if it's hydrophilic. The water molecules can surround the different components of that compound and break it down and dissolve. If it is hydrophobic, the water can't get in there and break it apart as well, so they just separate. Another important feature of water is that water is neutral when it comes to the pH scale. Water is neither an acid nor a base, and that's because if it were to dissociate or ionize, if it were to break down into ions, what we would have is a hydrogen ion. We'd have one of those, and we would have one hydroxide ion. So think of it, remember that water is H2O. So if it were to break down into its ionic form, what we would find is that these two ions would be equal. And so this is what makes water neutral. It's not going to register as either an acid or a base. Now on the pH scale, this is a scale that measures how acidic or how basic something is. And it ranges from 0 to 14. Water is going to be smack dab in the middle, okay, at 7. Now this is going to be pure water, okay? If you start talking about tap water or water that has solutes in it, it's going to slightly vary that neutrality, and it's going to either make it basic or acidic depending on the substances that are dissolved in that water. But if we're talking pure distilled H2O, it's going to be a 7 on the pH scale. And so what the pH scale actually measures is the hydrogen ion concentration. And I don't know all the math behind it. It's been a long time since I've done it. You may, I'm sure, did calculations in chemistry, but it has to do with a logarithm of the concentration of hydrogen ions in a solution. And that's where the numbers come from. And so different substances are going to release or take on these ions in a solution. And so acids are the substances that release the hydrogen ions. And so they're going to have a greater hydrogen ion concentration than a hydroxide ion concentration. And on the pH scale, these measure less than 7. So anything less than 7 would be considered an acid. And the further away you get from 7, the more hydrogen ions there are, and the stronger that acid will be, okay? Now bases are going to do the opposite. They're actually going to release hydroxide ions, or they take the hydrogen ions out of the solution. And so what happens is bases are going to have a greater hydroxide concentration. And so these are going to measure greater than 7 on the pH scale. And like the acids, the further away we go from 7, the more of those hydroxide ions they are, and the stronger that base is going to be. And so as we move up and down the scale from 0 to 14, with each step there is a 10-fold increase in the concentration of those ions. So the more acidic it becomes 10 times, 100 times, 1,000 times, and it's a 10 times fold every time. Okay, so we're talking a significant difference in the concentration of those ions. Same thing with the bases. We're going to see an increase in hydroxide ions with the 10-fold increase as we move up the base scale. Okay, so just know that those changes are significant, and there's quite a large difference of ion concentration between just one number on the pH scale. And the last thing we're going to talk about are buffers. You may have used these in chemistry when you did certain labs, but we definitely see this with living things because we know that living things need to maintain homeostasis. And one of the things that we need to keep relatively stable is pH. And that's going to involve pH just like in our cytoplasm. That's going to involve pH in substances like our blood. pH is really important because when we get to enzymes, we're going to learn that like temperature, pH can affect the shape of our enzymes. And so buffers are substances that kind of keep pH stable. They take on excess ions to prevent major changes. And so what they do is they just help maintain a steady pH and therefore keep these extreme changes from occurring. And so they are definitely very important in substances like our blood. And if we did not have these buffers, we would suffer some pretty grave consequences. And that is going to wrap up our second lesson for chemistry on the properties of water. Now coming up, you're going to have a little review activity to do just to kind of review you on some basic vocabulary and some practice questions to help you understand chemistry and properties of water a little bit better. And then here in a couple days, you're going to have a quiz on these. So if you guys have any questions, be sure you're getting help with those things, and hopefully I will see you soon. Y'all have a great day.